Okay, so welcome everybody to this afternoon session. It's my pleasure to chair this session with an invited talk by Sylvain Schmitz. Sylvain did his PhD in 2007 at the University of Nice, which was about parsing technique and ambiguity detection in programming language syntax. Then after 1 year postdoc at INRIA in Nancy, he became an associate professor at INS in Paris-Saclay. And since 2019, he is a full professor at University of Paris. Now he made multiple very interesting and deep contributions in the fields logic and verification. And he's in particular famous for his work for the verification on infinite state systems. This includes vector addition systems and other types of systems. And this talk, will somehow go in this direction. It is about branching in well-structured transition system. So please start. Thank you.
Thank you very much, Christelle, for the very nice introduction. And thanks everyone for coming to this talk. Thanks for the organizers for managing to do all this in those very difficult times. I apologize in advance if you hear some background noise from my ventilator because Zoom is a big CPU hog and okay, sorry about that. And let me get started. So the talk is about indeed branching in well-structured transition systems. So let me tell you a bit what the talk is going to be about. Those well-structured transition systems, WSTS from now on, it's a very general, broad algorithmic framework for decidability that has been around for quite some while. And I will spend quite some time reminding you about this. So if you already know about it, well, it's always nice to listen to things you already know. And if you don't know about this, well, it might be useful for you. I will spend very little time, but this is one of my motivation, which is complexity analysis for those well-structured transition systems. Technically, this goes through a notion of controlled batch sequences, and then you get very bad complexity bounds in terms of sub-recursive functions and so on. So I will just give a glimpse of what happens in that respect. And then I will go to the new stuff. Well, it's not really new because everything I will be talking about is sort of known, but maybe not so broadly known, only in some areas and not others, something like this. So the topic is how can we extend the notion of well-structured transition systems to the branching case, like some kind of tree or alternating automata, something like this. And I will use two examples that really come from logic. One is a fragment of XPath. So this is some kind of data logic, and the question is about satisfiability, and it's not trivial at all. Another one is a quite classical, actually, question about various relevance logic. So this goes back to an old paper by Sol Kripke in '59. And it turns out that one of the reasons probably why WSTS have not been much considered for branching systems is that actually what you can do is just take your branching system and sort of lift it to a classical well-structured transition system, so something which has a linear execution. But the problem is that the complexity analysis you might get if you try to do that might not be optimal. And I will look at one particular case of one of the decision problems for which you might want to have an algorithm and analyze this algorithm, where you can get better bounds if you look at things more closely and to not lift things to a linear system instead. So again, I think pretty much everything is known in some form or another. Hopefully there are some things which will still be somewhat elegant or surprising, even for people who know already a lot about well-structured transition systems. I also know that using Zoom is not so easy to ask questions, but still feel free to maybe write something on the chat or try to interrupt me if you manage. So let's get started with those well-structured transition systems. So as I said, this is a really general framework, an algorithmic framework. So it allows you to define generic algorithms that are going to be able to be applied to a large number of cases. Those algorithms typically look at various verification problems for transition systems like safety verification, or maybe you could look at simulation relations, termination properties, and things like this. And the underlying common theme in all those algorithms is that you're going to use the fact that there is a well Quasiorder somewhere, and that this well Quasiorder is going to guarantee termination. So this has been really successful. It's been around for quite a while. And in particular, in those two papers by Alain Finkel and Philippe Schmogelen and Baloch Aziz Abdullah, Carlis Gerans, Bengt Johnson, and Yi-Kun Tsei, which were, those two papers were awarded the Carver Award in 2017 for, well, all the contributions that have flowed from this framework in the field of automated verification and finding decision procedures for a lot of things. Really. So let me give you an example. This is really the example that everyone gives from the start. It's lossy counter machines. So, you know, Minsky multi-counter Minsky machines, right? You have a finite number of counters that range over the natural numbers. You can increment, decrement, well, not go below 0 because those are natural valued counters, and you can also test for 0. So Minsky machines, or pretty much everything is undecidable about the behaviors of these machines. But in lossy counter machines, we have a different semantics, which is lossy semantics, in which you're going to be able to apply, like here, a transition from Q1 with the configuration of the first counter 0 and 2 in the second counter, go to Q2 1 1 by adding 1 to C1. And this seems counterintuitive maybe, but actually what you do is start losing a bit or nothing, possibly, on each coordinate of your counters. Each one of your counters might lose something. Then you apply the transition, and then you can lose again. And in the same way, for this zero test transition here, for instance, you might lose this one value here, then indeed you can do the zero test, and then you can lose some more if you want, and you reach this new configuration. So this is a relaxed semantic somehow of Minsky counter machines. And it turns out that this is really classical model of well-structured transition system. So how can we analyze this kind of thing? So first of all is the problem we are looking at. We take a lossy counter machine, an initial configuration and a target configuration. And somehow this is a safety question. I would like to avoid reaching something greater or equal to that configuration. So does there exist a vector which is component-wise larger than this target vector, such that I can reach in finitely many lossy steps this target state and this new vector here greater or equal to the target vector. And in the case of lossy counter machines, actually this is essentially equivalent to reachability in the system. So this is one of the most studied decidability question for well-structured transition systems. And the algorithm for this actually dates back to the late 70s, where it first appeared actually for a slight variant of this called reset counter machines. And it's called the backward coverability algorithm. So I will run this on my example, and let's see whether I can cover this configuration where I'm in state Q2 and first counter is 1, second counter is 1, or more than 1. So can I cover this or get something larger? And the idea of this backward coverability algorithm will be to build, to compute successively a sequence of sets UK, which is the set of all those configurations which can cover my target here, Q2 1 1 in K of fewer steps, right? And then I will just have to check whether some in my initial configuration, which I don't even write here, does it belong to that set or not? So by induction of the K, I will start with K equals 0, and I will represent here the current contents of U naught, right? So it just contains Q2 1 1 because after the 0 steps, well, that's all I have. But actually, anything larger or equal to Q2 1 1, sorry, is also good, right? Anything larger or equal is covering in 0 or fewer steps. Now, if I want to look at what happens in 1 or fewer steps, I can look at, well, which transitions go into Q2. Actually, there's only one. So let's see which configurations could go inside that set U nodes. And I can see that Q1, 01, reaches lossily Q2, 11. And actually, anything larger or equal to this is going to also go into that set and nothing else. So my new set U1 is everything that I had before, U node, plus the upward closure, everything which is greater or equal to Q1, 01s, meaning the same control state, larger or equal values for my counters. And I could repeat this process again and again. For instance, what can reach Q1, 01? Well, I cannot come from Q2 here if I don't have 0 on the second counter. That's not the case. So the only possibility is to come from Q3. And then if I really undo the plus plus, right, I go backwards, then I find out that actually in 2 or fewer steps, this is everything that I can get. And I can keep applying the same kind of reasoning. At some point, I might notice that there are several configurations that go into a set, but sometimes I already had them, like this Q310. It goes in there, but I already had it inside U2, so there's no point in adding this new configuration. Now I can keep going like this again and again, but you noticed here that after 6 iterations of these algorithms, well, I have everything. So every configuration actually manages to cover the targets in some finite number of steps. So what have we built, really? We have built a sequence of sets where the initial set is the upward closure of the targets, and then at every step I took the previous set and made the union with all the existential predecessors. What can reach something inside the set UK? It turns out that this defines a sequence of upwards closed sets. So if I have something in the set and something larger or equal to that, then it's also in the set. And it also builds an ascending sequence, because every time my set is growing. And this ascending sequence, because we are going to be on the Quasiorder, well, it has to be finite. One of the reasons why it has to be finite, by the way, is this particular sequence here of configurations that I have written. This was defined by picking initially first configuration Q211, and then at every time, if you notice what I did, it was take something minimal, one of the minimal possible configurations that allow to go in there, and which is new, something which was not already computed. And this turns out to define something called a bad sequence. I will remind the definitions later, and this has to be finite over Quasiorder. Okay, so what about Quasiorders? First, a Quasiorder, if you're not familiar with this, it's just a support set along with a transitive and reflexive binary relation over it. Some of the notations I used before in the example, like upward closure of the set is everything in the set plus everything larger or equal to that. And when I have a singleton set, then I just write upward closure of one element directly without the curly brackets. I said it's upward closed if, well, its upward closure is equal to itself. And a sequence of elements, it can be finite or infinite over X, is called bad if for every pair of indices where I is strictly before J, Xi is not great. Sorry, it's bad if it is actually. This is good. Wait, no, sorry, I'm confused now. This is bad, and good is the sorry. Today. Okay, so a Quasiorder is a Quasiorder if all the bad sequences are finite. And there's a lot of equivalent characterizations of this notion, which is really very robust. For instance, ascending chains of upward closed subsets are also finite, or also equivalently, you have a finite basis property that tells you that if you take a non-empty set, then it will have a non-empty set of of finitely many minimal elements up to equivalence. If you're working over quasi-order, you could have elements which are equivalent for the ordering. Still equivalently, well, this order is well-founded, meaning you don't have infinite strictly decreasing sequences, and also you don't have here any infinite anti-chain in addition to being well-founded. And you have quite a few more. This is, as I said, a very robust notion that appears in many places. And it's quite convenient. So here are some examples. For instance, every well-founded linear order, well, it doesn't have any anti-chains of size greater than 1, and it's well-founded, so it has to be a well-quasi-order. Another way to see this is that a bad sequence is actually a strictly decreasing sequence in this well-founded linear order, so then it has to be finite. So if, for instance, the set of natural numbers with the usual ordering is going to be a well-quasi-order. Another example is of a way to build new well-quasi-orderings from known ones is through products, where you use the product ordering. So component-wise, if you have a well-quasi-order on the first component and one on the second component, and you use the component-wise product ordering, then this will build your WQ. And one example is the case of lossy counter machines that we had before. Essentially, what it was a configuration in those systems that was some state inside a finite set of states where equality is used as the quasi-ordering, and that's fine because it's a finite set. So this is a WQ. And then times n to the d, where d is the number of counters, and with this product ordering. So this is going to be one quasi-order. Now, what about well-structured transition systems? Essentially, you have 3 ingredients. You have a transition system, so a support set with just a binary relation, but it's also order, so you also have a quasi-order in there. A second ingredient is that you need some kind of compatibility between your transitions and your order, your quasi-ordering. So it's called here the upward compatibility, which says that whenever you're in a situation where you have an element X that can do a transition step into an element Y of your set, and X happens to be less or equal to X prime, then there's a way to somehow close this diagram and find a Y prime, which can be reached by X prime in one step, and is greater or equal to Y. And then there's a lot of variation around those compatibility notions. Here in this talk, actually, I will work with reflexive compatibility, which means that I can also choose Y prime to be equal to X prime in the case where X prime is greater or equal to Y, and that's also fine. So I will say compatibility, but I will mean reflexive compatibility most of the time in this talk. And the third ingredient in order to have a WSTS in the definition is that, well, X and this quasi-ordering should be a well quasi-order. So one example where, again, lossy counter machines, because of these lossy transitions, you can see that if I have a configuration here that lossily reaches Y and have another configuration which is greater or equal, where I can just lose and go down here and then do the transition to the configuration Y. So Y prime equals Y will work. So that's an example that's showing you that lossy counter machines are well quasi-orders. So the compatibility problem I gave earlier can be generalized in this framework. Whenever you have another transition system with an initial configuration and target configuration, you can ask, is it the case that I can reach after finitely many steps some configuration which is greater or equal to my target? And this compatibility problem, I should say, this is modulo some hygienic conditions that are typically enforced, but of course you can build crazy examples using Turing machines and so on where it won't work. But in practice, in the way people use it, it works, and those conditions are enforced. In that case, compatibility is decidable for well-structured transition systems using exactly the backward compatibility algorithm I showed you earlier. And you can, if you remember, this algorithm terminated thanks to the ascending chain condition, or alternatively, you could extract this sequence of minimal predecessors at every step, and this will build you minimal bad sequence, so it has to be finite as well. So termination is enforced through the Quasiorder. A variant which will be used in this talk is called downward WSTS, where you modify slightly the compatibility definition. Instead of being in a situation where x was smaller or equal to x prime, now it's reversed. You're in a situation where x is greater or equal to x prime. And now you want to close again and find some y prime, which is smaller or equal to y and can be reached from x, or possibly could be equal to x prime also. And the decision problem that people want to solve in this situation typically is a sort of a dual somewhere. It's the subcoverability problem, and now the goal is not to cover the target, but to subcover it, meaning to be able to reach some t prime, which is smaller or equal to the target. And again, modulo some conditions, sanity conditions that you need, but which are typically hold in the examples people study. This is going to be decidable for downwards WSTS, and somehow you're using a variation over the backwards coverability algorithm, but this time it's going to go forward. But it's again a saturation algorithm that terminates thanks to the assembling chain condition. All right, so that's, oh yeah, I had an example. Actually, if you, instead of using lossy counter machines, if you had incrementing counter machines, meaning that at every step you can first have your counter value grow, and then do the actual step of your Minsky machine, and then you can grow again your counter values, then this will give you, for the same reason as before, downward compatible WSTS, and then subcoverability is going to be decidable for those machines. Okay, I think that's it for well-suited transition systems, and now we come to one of the motivations for what will come next, which is complexity analysis for this. So I hope you agree with what I've said, that the termination of those algorithms really rely heavily on the WQ, right? Essentially, you can look at this ascending chain condition, but from an ascending chain, you can always extract a bad sequence. So really what is happening is that the length, somehow the big running time of your algorithm, if you neglect how hard it is to extract some predecessors and so on, is going to be how long those bad sequences are going to be. We know that they are finite, but how long can they be? Well, actually, they can be of arbitrary length. So if you go over L square, here's an example where you start in 0, 2, and now I'm not allowed to be greater or equal to that point. So the red area is forbidden. I have to pick my points for the rest of the sequence below, okay, in the white part. But okay, I can pick 2, 1, and maybe 0, 1, and now I have to pick something along the horizontal axis here. So why not 6, 0? And then, well, now I don't really have much choice. I have to pick smaller and smaller things, and this is a bad sequence. But actually notice that at this particular point, when I picked 6, 0, I could have picked 10, 0, 1,000, 0, 1 million, 0, and I would have longer and longer bad sequences. Thankfully, what happens in those algorithms on structured transition systems is that, and also in other algorithms that rely on well quasi-orderings, is that typically those bad sequences are not arbitrary. And what happens is that if you add a notion of size somehow of your elements, or a norm that you put over your quasi-ordering, and you add the fact that somehow along your bad sequences, well, your elements cannot grow arbitrarily. So if you think again about my backward coverability algorithm, I was building this bad sequence of somehow minimal predecessors, right? So those minimal predecessors, they could not grow very fast, right? Because if I take a predecessor of something, at first, if I have a minimal predecessor, at first, what happens is that I did a decrement, right? So at first, I increase one of my counter values. So that's really not much. And essentially, this captures this idea. So that is, my sequence here is controlled by some function g and some initial norm and nodes. If at step I, and the size of my ith element is at most g iterated I times, of n nodes. So notice that if I equals 0, in that case, this means that x node, its size is at most n nodes, so that's why I call it the initial norm. And then somehow you can grow, but not too fast, right? You can iterate somehow, growing by g again and again and again. It's a bit amortized as well. So what happens when you do this is that in addition to having the red zone where you're not allowed to go in order to have bad sequence, you also have to stay inside some green area, which is the area using of the control, right? So here I'm using the infinity norm for n squared, so I just take the max of the two coordinates. Initially, I take n node equal 2, and then I will grow one by one. So what happens in the previous example, I can start somehow in the same way. My control is growing slowly, but notice that at the point where before I had 6, 0, now I have 5, 0, and this is really the most I can do at that point. And now I have to finish like this. So what happens in practice is that in a Quasiorder, if the set of elements of a given norm is finite for every n, then those controlled by sequences, they will have a maximal length, and we can give it some notation here to denote this length. So thanks to the control, there is a maximal length. And now what has been developed by many people, really, are so-called length function theorems. So those are combinatorial results that give explicit upper bounds on that length here for various Quasiorders. And those bounds are given in terms of some fast-growing functions, let's say f alpha. I will tell you what f alpha is. It's actually related to the Ackermann function and things like that. So this is the definition, one of the possible definitions, because all these are a bit flexible. That comes from Loeb and Biner. So initially you take like the successor function at rank 0, and then each time you add 1, what you do is iterate x plus 1 times, or x is your argument, the previous function. So if you do that for f1, you will get this is equal to 2x plus 1. But then if you iterate multiplication by 2, roughly multiplication by 2, what you will get is something a bit larger than an exponential. And now if you iterate an exponential of exponential of exponential, what you will get is a tower of exponential. And now you can keep iterating like this, plus 1, plus 1, plus 1, and at some point, when you reach here x plus 1 in the index, this will give you, by some kind of diagonalization, this will give you something which is akin to, there are several definitions of Ackermann. You might as well take this one, actually. So this is like the Ackermann function. But it's not over, you can actually keep going, like 2 plus 1 again. So this means iterating the previous function x plus 1 times. You can do plus 1 plus 2 and so on. And then you can do times 2 by adding plus x plus 1. Maybe you can do times 3 by using omega times 2 plus x plus 1. And you can go to omega squared, which is omega times x plus 1, and so on and so forth. You see, you can really diagonalize and get larger and larger ordinal indices. So those are really fast-growing functions, and they allow you to define some corresponding complexity classes, and those complexity classes turn out to be quite adequate to look at the complexity of problems of a Welsother transition systems. In particular, compatibility is f omega complete for those lossy counter machines. So this is like Ackermann complexity, really. And then you get other models like those new Petri nets. They have f omega times 2 complexity, or f omega times 2 the omega, sorry, complete for another model of lossy channel systems and so on. So it turns out that those complexities are actually quite relevant when you want to look at Welsother transition systems. Right, that's it for my big reminder about Welsother transition systems. Now I would like to go to branching systems. So essentially, I will just define them very naturally by saying, okay, I have a transition relation, but now instead of being of a pairs or from one element of my set to one element, now it goes to a set of elements. And I might say already for quite a few things that I will do later, I will actually require that this is a finite set, but for some other things, I actually need that. So I won't always be very precise about whether they're finite or not. So this definition gives you a notion of tree execution, right? Where if at a node I have x and x goes to some set, y1, y2, and so on, then I can have y1, y2, and so on as the children of my element x, and then I can keep going. And it can be ordered by adding again a quasi-ordering here over my sets. And then we can look at various coverability problems. So if you're given an ordered branching system, now a root configuration and a leaf configuration, then you can have various variation around coverability. One could be leaf coverability, where you start with the root configuration and you want that every leaf is greater or equal to your target leaf configuration. So you could also call this top-down coverability, right? But then you can go the other way around, where you start from your leaf configuration and now you want to go up to the root, and get something which is greater or equal to your target root configuration R. And now you can also do subcoverability, meaning that instead of going down and trying to be greater or equal to L, you want to be smaller or equal to L on every one of your leaves. And you can also do root subcoverability, meaning that now going up, you want to get something at the root, which is smaller or equal to your root configuration. I might mention also that all those coverability problems, you could have variations like having a finite set of root or leaf configurations, doesn't change much. You could also have, depending on whether you're doing coverability or subcoverability, you could also have upward closed and downward closed sets. It also generalizes well. Okay, so let's see now some examples of questions that can be modeled using such branching systems. So one comes from, motivation comes from forward XPath epsilon. Okay, this is a fragment of, let's say, a theoretical fragment of XPath. So XPath appears inside various kinds of documents that are used for processing XML files. For instance, XSL documents like this here, you have some XPath going on around here inside your document. Also in xquery, you have typically, when you can see some stuff going on here again. So this is a language, selection language really, that allows you to select node inside XML documents, which is embedded into other programming languages or other querying languages. So the idea is that starting from an XML document, you're going to be able to select some node inside your document using some XPath expression. So your XML document really is an encoding of a tree because it's hierarchical, right? You see you have opening tags, closing tags, and so on. So this gives rise to something which is called a data tree, like this one. And I can show you on this example how this XPath expression is going to be evaluated. The beginning here tells you go down from the root to some nodes labeled F. So for instance, this one. Now you will select this node F if the condition between those brackets is satisfied. So what's going on inside those brackets? I want the two things have the same value. So on the one hand, I will have that some attribute A has some value, and on the other hand, I have to follow a full path here that does something first. So what does this path do? It does nothing first, then goes down to something with an H, then goes right. So down to something labeled H, and then goes right to something labeled F. And now we'll look at the value of this attribute B, and what we want is that the value here of attribute A is equal to the value here of attribute B. So since this condition is satisfied, this means that this XPath will select this node F here that we had before. Okay, so what is done in that paper by Marcin Godzinski and Rojko Lazic is to show that satisfiability for a fragment of XPath. So forward meaning that you can go down and go right, but not left or up inside your data tree. And epsilon is about the fact that here one of the two sides of the equality sign was, I just stayed where I was, I just looked at one of the attributes here. And while this fragment Satisfiability actually reduces to emptiness in some kind of alternating tree automata that will process your trees, but this tree automaton will have one register to store and compare data values that it has seen along the way. And then by applying some kind of counter abstraction, where the idea is that you want to count how many different situations you might be in with your data values, so how many different data values for each situation you need. You will be able to reduce it to a subcavality problem to something called incrementing tree contamination. So this is what is shown in that paper by Martin and Ranko. And actually this framework, I would say, has been extended to other larger fragments of XPath, in particular by Diego Figueira. So if you're interested in the topic, there's this survey here in Signal News by Diego. So what are incrementing tree counter machines? They are really a natural extension of incrementing counter machines. So it looks like a Minsky machine, but some of the transition may be binary, right? So here you will do C1++, and then you will spawn one copy that will go to Q1 and another copy that will go to Q2. So if you look at now an execution of this system, and I developed the incrementing semantics so that we see everything going on. So you start, for instance, in Q1 02, you first grow a bit because you have incrementing semantics. Then you apply C1++ and you fork, somehow you fork your configurations. One will go to Q1 12, the other will go down here to Q2 12. Then on each of those two branches, of course, you can increment again if you like. Then you can apply a transition, for instance, here this C1 and then you can grow again if you like, and so on. So it turns out that subcavality in those incrementing tree counter machines is decidable, and thus because Martin and Ranko showed that there was reduction from the satisfiability problem for this logic to that problem of subcavality, then satisfiability from decidability of satisfiability also follows. All right, that's it about those XPath fragments. Another example will come from something quite different, but also related to logic. So this is proof theory, really. And it's about several relevance logics. So the idea behind relevance logic is that when you do reasoning using implication in particular, you want that the hypotheses of your implications are actually useful in that reasoning. So for instance, this is a theorem of classical propositional logic. A implies that B implies A, but if you think of it in terms of natural language, this seems a bit weird, right? So for instance, if it's raining, then if your favorite color is green, then it's raining, is a weird sentence semantically somehow for human beings. And in relevance logic, actually, this will not be a theorem. This will not be accepted because this B here is, this hypothesis is never used, really. So the way you can translate this intuition is through a sequent calculus. So this will be some kind of intuitionistic-like sequent calculus. And in this calculus, where here I just have the implication symbol, the important point is that I do have contraction, but I do not have weakening. So somehow the rule of weakening, the structural rule of weakening, is the one that allows you to just let any hypothesis pop inside your formula and make it valid inside classical propositional logic. By removing weakening from the system, you get something which is the implicational fragment of relevance logic. So this was shown by Song Crick in 1959 to be decidable, and it's actually a very interesting proof, and I will talk quite a bit about what's going on in there. It's been extended, the whole technique that Crick used in that abstract has been adapted and extended to larger and larger variants of relevance logic. For instance, you have something which is called LR+. If you look at this system, if you already know linear logic, well, this implication here is really linear implication in intuitionistic linear logic, right? And then LR plus is really just adding the symbol of rules for multiplicative conjunction, additive disjunction, additive conjunction, and the one constant. And this LR plus, well, is decidable. This was shown quite early on, actually, by adapting the proof argument of Kripke. And then later on, people noticed, in particular in this paper by Jacques Rich and Robert K. Mayer, that this is actually about one quasi-orderings. That's what's happening inside Kripke's proof. So let's see how to do that. But first, let me mention that a big result, I think, is about complexity now, is in this paper of Alasdair Lookwart, who showed complexity results for LR+. I will mention this further. So how do you get to well quasi-orderings? So first, something which is often true of those proof systems, because you have cut elimination, you don't need the cut rule. Then after that, you have the subformula property. In every rule, if you look at the formulae that appear on top of your rule, right, in the premises, then those formulae are subformulae of those rules that were in the conclusion. Which means that in proof search, where you start from some sequence here, and then you try to develop a proof tree like this and close every branch by having an instance of some of the ID, right, the axiom rule. In this proof search, you will only need to work with formulae from the finite sets of all those subformulae of everything that appears in this multiset gamma and the formulae A itself, right? So we are going to be working over a finite set of possible formulae. Now, from a sequence, so here this is a multi-set of formulae, right? And here this is a formula. We are going to associate an element with the encoding of this sequence, where I will put first the domain of this multiset, so just the set of elements that appear at least once inside this multiset. Then a vector here V delta that will count for every formula how many times it appears in the multiset. And then this formula B, which is on the right of the turnstile. So this is an element of power set of sigma, but this is a finite set, times n to the size of sigma, but this is finite, right? Times sigma. So this is a product of 3 WQOs, and it's a WQO by Dixon's lemma. And the ordering, the product ordering that you get on this, right, if you look at encodings, this product ordering, it holds exactly when this sequence here can be obtained by the second one if you contract things inside here. So somehow if you have duplicate formulas, you can remove one of the duplicates, but you cannot remove one entirely. That's why you have to have the same domain here of your multisets. Then what happens is that proof search for a sequence is going to be an instance of leaf subcoverability, where at the root here, you will put the encoding of the sequence, and at the leaves, you will try to be covered by instances of the axiom rule, really. And if you are covered by instances of the axiom rule, well, nothing can cover this except itself, so you will win. Okay, so about those two examples, it turns out that they are both known to be Ackermann hard, right? So satisfiability of forward X path on the one hand, and provability in this relevance logic, which looks a bit like really multiplicative, additive, linear logic with contraction. Now, how to solve those probability problems using well-structured transition systems. So the first, what we will need is a way to lift WQOs to power sets. So we want to build linear systems, but that will be working on sets of configurations, actually finite sets of configurations in practice. So we have two tools for this. Actually, there are two natural quasi-orderings Here I write ordering, but I really mean quasi-orderings because in general it's going to be a quasi-ordering. The first one, called the Hoare ordering, is going to say, well, S is more or equal to S prime if for every element here I can find an element there which is greater or equal. And then for the Schmitz ordering, it's the other way around. For every element in this larger set for this ordering, I can find something smaller or equal here on the left. So now finite subsets of X using this quasi-ordering here is going to be WQ. However, the finite subsets of X using this quasi-ordering is not going to be a WQ in general. So this is a well-known situation that was, and the canonical counterexample actually comes from a pretty old paper by Haddo. And it's, if you want to learn more about this, well, it's omega squared WQ. It's an extension of WQs, really. So it's a restriction of WQs, I should say, which is exactly those WQs where you can take the power sets, finite power sets, and order them using the Schmitz ordering, and it will work. And you can also have a look at this paper by Peter Janschar, who showed that, well, this works exactly when you don't embed some particular quasi-ordering, which is called Pareto's example. Okay, so now let's come back to my covariety problems. I had 4 of those. And for each one of those, I will have a notion of compatibility that will work out. So for instance, for leaf covariety, it turns out that a good notion of compatibility for branching systems is going to be this one. If from X I can go to a set S and have X prime larger or equal, then I should be able to go to a set S prime, which is greater or equal, but for the Schmitz ordering. And then, interestingly enough, when you go to the other examples, you will see variations where you switch to the Hoare ordering. And for subcovariety, you will switch again somehow. So leaf covariety was with Schmitz, but leaf subcovariety will be with Hoare ordering. And here you see that it will be with Schmitz quasi-ordering. So there's, I don't know, everything sort of works very nicely in this framework using those 2 ways of lifting quasi-orders to power sets. I will focus here on leaf subcovariety because the 2 examples I gave before, right, of XPath and relevance logics, those were leaf subcovariety problems. So in order now to lift my branching system to a linear one, I will have something reasonable notion here of transitions between subsets, right? We said that S goes to T if T can be written as a union of Tx, where for all X in S, where at every step, right, X will go to Tx or just stay itself. So, I mean, implicitly it goes to the singleton X instead of going to something new. Okay, so essentially this describes that you, starting from the singleton in the root, you can go to a set S whenever S is the set of elements you can see along cuts in an execution tree. And now leaf covariety, so you want to have every leaf greater or equal to L, is the same as saying, well, can you reach a set S which is greater or equal for Schmitz to L, which means that for all elements of S, well, you have to find an element here, so you don't have a choice, it's L, which is smaller or equal, so that's good. And leaf subcovariety is now going to be somehow a dual using Hoare. You want that for every element here in that set, there should be something greater or equal. It should be greater. So for top-down downward compatibility, which was the condition I gave earlier, it turns out that an ordered branching system has this compatibility condition if and only if the lifted system, the one where you use power set here, you use the Hoare ordering here, and you use this lifted transition relation that just goes down possibly on several branches at the same time. And so you're in really, I don't have time to look at the proof, but it's fairly straightforward that this works out nicely. And now, what happens for incrementing tree counter machines and my sequence calculus? So for incrementing tree counter machines, it's really straightforward. This will satisfy this top-down downward compatibility condition. However, the sequence calculus does not satisfy it. So the example, this is a very easy example. You see that from this sequence, I can apply the left implication rule that goes here. But if I look at a smaller sequence, so one where I have one fewer instance of D, so then I won't be able to put one D on the left and one D on the right. So I won't have the same support for the same domain for my multiset here in those branches. So that doesn't work. This is not compatible, but this has been seen already back in Kripke's paper. What you can do is replace your left implication rule with a rule with built-in contraction. So this is a bit informal, but I hope you can understand. This denotes the fact that this is a multiset of formulae which can be obtained from that multiset here by contraction, essentially. Okay, and of course, this, if you replace the left implication rule by this new rule, everything that was provable before is still provable, and vice versa. So you have an equivalent system, but this new system now does satisfy this downward compatibility. So everything is good and fine. So now we can apply length function theorems because, well, we want to get complexity results. And here we have very recent results by Balasubramanian, who very recently, at least last year, showed complexity upper bounds which are pretty tight actually for the length of bad sequences over finite subsets of n to the d. And by pretty tight meaning that he could show that there exist bad sequences which are controlled and over these, which essentially go up to those gigantic bounds, right? But this yields f omega to the omega upper bounds, whereas the lower bounds we had were just f omega. So that yields a very big gap. And what happens here really is that this is really quite tight, but this is in a system where those subsets of n to the d do not have to obey the transition relation of a branching transition system. And it turns out that I think in most cases, you don't have to go through lifting your system in order to get complexity. In particular, Alastair Oakwood showed back in 90, by analyzing the decidability proof of Kripke, this principle to prove the extension of it really to this system, and using a length function theorem for vectors of natural numbers by McCallum, that actually this is in F omega. This has Ackermann complexity, and since in 1999 he also showed that this was hard for Ackermann, then this is actually complete. And here is the idea behind all this. So this is really the idea of Kripke's procedure, but adapted to a more general case of branching systems for subcovariety, top-down subcovariety problem. So a witness of subcovariety will be something like this, right? You start from the root and you want to find an execution where every leaf here is smaller or equal to your target leaf configuration. Now inside this witness you have nodes like this, where the set of successors here of children of your node is taken. It's exactly the set of successors in the branching transition system. Now we can have something slightly relaxed, which I would call pseudo-witnesses, which is to say that, well, actually you could, instead of taking x and then doing the transition, you could take x prime, which is greater or equal, and then do the transition. And that's okay because of compatibility. Somehow, if you think of it like some kind of strategy, right? You want to have a strategy against your opponent who chooses one of the branches as you go. You want to be able to get somewhere less or equal to L. Having something, if you can win with a greater x prime here, then for sure you can win with the smaller one by compatibility. So that's, if you can win with this notion of pseudo-witness, then you also have a witness. And of course, a witness is a particular case of a pseudo-witness. So this is equivalent. Another way of restating what I just did is to say that I can pick a set here which belongs to the set of all sets that can be reached starting from the upward closure of X in one go. Right? Exactly the same definition, but stated differently. So those will be my pseudo-witnesses. Now, I want to build irredundant pseudo-witnesses. There will be two conditions. One is that along a branch, I'm not allowed to find some X prime a bit later, which is greater or equal to X. Because otherwise, well, I can just completely take out the subtree that was rooted in X, replace it by the subtree rooted in X prime, and by compatibility, everything is still working because here everything is smaller or equal to L, here everything is smaller or equal to L, then I can do that. This is still a pseudo-witness, and it's a smaller one, definitely. Another possibility, another simplification I can make is that I would like to take here, among all those sets of children here, I want to take a set which is minimal for this whole ordering. And again, this is because of compatibility, this is fine, I can guarantee that I do that. In particular, notice that when I use the compatibility definition, then my paths do not grow longer. They can go shorter, but no longer. So that's also good. So I can always assume that my pseudo-witnesses enforce those two additional conditions, right? You have bad sequences along branches, and you take your successors along minimal sets. Thus, there exist redundant pseudo-witnesses if and only if subcovariety holds. The sequences along the branches are bad sequences. And because along my sequence here, xi plus 1 is going to be in some set which is minimal for ordering along the way, we are going to be able to control those sequences in typical applications. Like, for instance, for relevance logic, you will be able to control how big this xi plus 1 is going to be. You still need a slightly bit more because you need to control this n branching degree somehow, right? That would be a problem if it were infinite. But okay, in the case, for instance, of the logic, but also in the case of incrementing tree counter machines, this degree was actually fixed. It was 2. But okay, otherwise you need something. And then length function theorems will allow you to bound the height. And because it bounds the height, it will also allow you to bound the norm of the elements inside your tree. And if you bound the norm of the elements inside your tree, you will be able to bound also the branching degree. And then in the end, you will bound the size of the whole tree. And it will tell you that those irredundant pseudo-witnesses, they have a bounded size. You can even compute all of them if you want. But you only need one in order to conclude about subcovariety. So that's it. So somehow I had the impression that there was a lack of systematic investigation of what happened in branching well-structured transition systems. I guess the reason was because for a long time we didn't really look into complexity for well-structured transition systems, and there's people who established decidability results for branching systems by lifting were pretty satisfied with this. But it turns out that it might not be optimal, really. And here in this talk, somehow it turns out that ideas that were already known back in 59 can be really generalized in a straightforward way to a slightly larger framework of branching WSTS for this leaf subcovariety problem. In a recent paper, jointly with Ranko Lazic, actually, we also gave sort of backward covariability algorithms for root and leaf covariability. And I think also that root subcovariability is pretty straightforward as well. So this is looked like it's more of a case of no one really looked into it much, but I kind of like this nice symmetry between Hoare and Schmitz. Somehow that I found that pretty nice. So thanks a lot. I hope you enjoyed this talk, and I would be very happy if you had any questions.
Thank you very much for this very nice, interesting talk. Are there questions? so maybe just start to ask, or I'll write something in the chat, because I do not see everyone.
Or raise your hand. I have allowed the participants to unmute themselves. So if you have a questions, maybe you can just start asking.
Maybe I can ask a question?
Yeah, sure.
So Sylvain, you explained that Urquhart already had a upper bound.
Yes.
Would you say that his proof was, quite complex and combinatorial, and that it's good to have, let's say, generic tools?
Yeah, so Urquhart had an upper bound, but the upper bound was based on this upper bound of McCallum. So what Urquhart did was essentially do the kind of analysis I sketch here, right? So because Kricker's proof is essentially doing what I sketched with this irredundant pseudo-witnesses. So what Urquhart did was look at the corresponding counter abstraction, and then McCallum gives upper bounds on the length of bad sequences of n to the d, also n to the d plus some finite stuff around is not a big problem. One issue, well, we both worked on this topic. We have other length function theorems that are in some ways improvements of McCallum. I actually believe in many ways, but it was still exploitable since, as you can see, Urquhart knew of this result of McCallum and also managed to use it to prove this upper bound.
Okay, thanks.
Well, I have a maybe very naive question. Well, you considered here coverability and sub-coverability.
Yes.
And in the beginning, so the instances you presented, these were channel systems with increments and lossy channel systems. If I consider channel systems that can increment at random and lose things at random, then
I think those should be pretty easy, no? Because what's to prevent you from reaching anything in that case? I don't know.
Yeah, you're right.
If you just do graph reachability in the control graph, I guess, unless I'm missing something.
You're right. But yeah, they can do everything. Yeah. Sorry. If I don't see any other question either in the chat. I might oversee someone raising the hands.
I don't see anyone, so I guess it's been a long day already.
Okay, so then before I close this section, Alex asked me to remind that there is a reception at 5:30 in the social room at Gether. Okay, let's thank Sylvain again.
Thanks a lot, and see you at the reception.
Okay.
Bye.
Goodbye.